Good afternoon, everyone, and welcome to the finals round of the 2019 National Quantum Matters Science Communication Competition.
When I saw the advertisement, I was actually pretty excited.
I had this cool demo that I'd already created and I wanted to share it with the world.
I think it's really important for scientists to communicate to public audiences.
It's just a way to give back to the community. It's the reason I became a scientist.
So the challenge is to see who can make the best 3-minute talk to a family audience explaining one key aspect of quantum science and technology and why it matters to us. Now, the 4 finalists who you'll see on stage today, they have done a fabulous job coming up with really fun and creative ways of helping you connect with the world of quantum technologies. Now, we think they're all winners, but we want you to pay very close attention because we're going to be asking you to help us pick the Audience Choice Prize winner. Basically, who does the best job in just 3 minutes of opening your eyes to some insight into the quantum world? Now, we also have a distinguished panel of judges. Judge number 1 is Joe Chikelsky. He is a professor of physics at MIT, where he studies and makes quantum materials. Judge number 2 is Dr. Diana Augie-Craik, who is a postdoctoral researcher at Harvard, where she explores quantum sensing in tiny diamonds. Judge number 3 is Evan Haddingham, who is the senior science editor at the PBS TV series Nova, where he has overseen the content of dozens of award-winning science documentaries. And judge number 4 is Dr. Brinda Muniappan. She is the Director of Education and Public Programs at the MIT Museum, where she helps faculty and students share their research with the community. Can I please have the judges stand and be acknowledged by the audience?
I'm going to be looking for some real energy on the stage and general enthusiasm about quantum physics and engaging others in that topic.
So I'm looking for the contestant who can really do the best job of taking that complicated idea and connecting it to a really common experience.
Well, I'm going to be looking for not only meeting the audience where they are, but also why should I care? You know, what has this got to do with our everyday lives and with our future too?
If you can communicate science to an audience and also make them laugh, that's brilliant.
And now I'm delighted to introduce to you the first Quantum Matters contestant. Finalist number 1 is a scientist working on quantum computing at Booz Allen Hamilton in Washington, D.C. Before that, he got his PhD from George Mason University, focusing in astronomy and computer science. And before that, he was just a curious kid from Lowell, Massachusetts, who enjoyed coming to this museum. Let's hear a round of applause to welcome Gideon Bass to the stage.
Computers have changed our lives. How we work, how we live, how we play. But think back to the 1950s. Computers were room-sized devices used only by experts with special training. In 70 years, we've gone from lab equipment like this to devices that we all use all the time. So what happened? I think one thing that has helped people adapt to this new technology so quickly has been the computer game. In 1972, Atari debuted Pong. It's a simple game, 2 players controlling paddles trying to hit a ball past the other side. But at the time, it was revolutionary, and it immediately became a huge success. Pong and the computer games that came after it, like Oregon Trail, SimCity 2000, and Minecraft, were many people's first interaction with computers, and also taught us a few things. So what does any of this have to do with quantum mechanics? I'm a quantum computing researcher and also a consultant, which means I spend a lot of time trying to explain quantum computers to people. Quantum computers today are a lot like regular computers were in the 1950s. They're large, experimental devices used only by trained experts. So when I was tasked with coming up with a cool, fun demo to showcase quantum computing, I decided to create a quantum computer game. I call it Pong. Pong is a lot like regular Pong. You have two players controlling paddles trying to hit a ball past the other player's side. But there's one key difference. In regular Pong, the ball is in one distinct location. In Pong, things are a bit more complicated. See this white line? That's the path we would expect the ball to take if this was regular Pong. But in quantum mechanics, an object is only in one distinct location when you're looking at it. That's this green dot. When you're not looking at it, an object can be in multiple places all at the same time. That's this red cloud. As you can imagine, this makes playing Pong a bit harder and arguably more fun. Imagine lining up the paddle to hit the ball, and the ball is somewhere else. Quantum computers use this uncertainty to enable them to compare multiple solutions to a hard problem simultaneously. I call Pong a quantum computer game because it doesn't just show this uncertainty. It uses a type of quantum computer, a quantum annealer, to calculate all of the possible trajectories the ball could take. In the future, I expect quantum computer games, like Pong, to be many people's first hands-on experience using a quantum computer and make their understanding of this technology a little bit more certain. Thank you.
Let's hear it for Gideon Bass.
I think it went pretty good. It was a lot of fun. I think there's a lot of audience engagement. I had a great time.
And now I'd like to introduce you to finalist number 2. She is a senior majoring in physics at Mount Holyoke College. Her undergraduate research combines both her interest in physics and in environmental sustainability. She grew up in China before coming to Canada for high school and then ended up in the US for college. And in the fall, she'll be entering graduate school at Brown University. Please help me welcome to the stage Sue Shi.
You're standing in the sun and starting to feel warm. That's because the sun releases energy packets called photons that are bumping into electrons in the atoms that make up your skin, making them jiggle and heat up. And some photons are much more energetic and can cause sunburns. So can we take the energy from the photons and convert it into electricity? Yes, that's exactly what solar panels do. Just like your skin, solar panels are also made of electrons. But in a solar panel, when a photon with enough energy bumps into an electron, it energizes that electron up to a higher energy level across an energy gap where electrons aren't allowed. And when the electron falls back down, it releases the same amount of energy as the gap, which is used by the solar panel to produce electricity. So you can think of the magnitude of this gap as the height of a hydropower reservoir on a watershed. A higher reservoir allows water to drop more forcefully, giving us more energy, but a lower watershed or a lower reservoir can harvest more water, giving us more current. And to maximize the power output, we placed reservoirs at different heights for different types of watersheds. Likewise, in the solar panel, we should use different energy gaps to absorb photons with different energies. But traditional solar panels are made of silicon, which has a fixed energy gap. And I researched next-generation solar panels with a mysterious quantum material that has an adjustable energy gap. And to see how that works, let's take a trip down to the quantum scale. And before we go, we got a pack. So we take spaciously laid out items from a closet and stuff them in a suitcase. In the quantum scale, we can take a free electron and stuff it in a quantum suitcase. The smaller the suitcase, the more confined the electron is, the more energy it could have. So by simply controlling the size of the quantum suitcase, we can tweak the energy gap. Sounds perfect, right? But wait a second. We also need current to produce electricity. Like when we flip on a light switch, we get current flow because electrons are moving in a line one after another. But if the electrons are now locked in suitcases, how do they move? Well, we're now in a magical quantum world where electrons behave like wizards that can tunnel through walls, literally. So when we have electrons tunnel from one suitcase to the next, we have a flow of electrons giving us current. But rather than placing electrons in suitcases, researchers place them in nanoparticles called quantum dots. And the size of a quantum dot is only a few nanometers. So we can suspend a gazillion quantum dots in solution and print out rolls of solar panels that are as thin as plastic wrap. And I hope that one day, in a sustainable future, you'll be on a camping trip appreciating nature while reading a quantum physics textbook in a tent powered by quantum dot solar panels. Thank you.
Let's hear it for Su Shi.
I think it went really well. They seem to be really into what I was talking about and moving along with me, so I think that was really good.
And now I'd like to introduce you to finalist number 3. He grew up in Kolkata, India, where very early on he discovered passions for science and mathematics, physics and computer science. Well, he combined those interests, and that led him to pursue the field of quantum information. That's what brought him to Canada. He is now a graduate student at the Institute for Quantum Computing at the University of Waterloo. Please help me welcome Aditya Jain to the stage.
Hello everyone. Today I'll introduce you to quantum computers through the story of two friends, Alice and Bob. Bob likes Alice. However, Alice is not so sure about liking Bob. So how do we represent this confused state of Alice? She is in a mix of these two possibilities. On one hand, she likes him. On the other, she doesn't like him. This mix of two states at the same time is called quantum superposition. Here, Alice represents a quantum bit or a qubit. Now, Bob is doubtful, and he wants to find out about how Alice feels. So one fine day, he overcomes his fear and asks Alice. The answer, as you might guess, can be a yes or a no. And once Alice answers, her state is fixed. This is what we call quantum measurement. A confused state goes into a measurement device, and a precise state comes out of it. But you may ask, what are the chances of either answer? The chances are dictated by the numbers beside these states. Let's say Alice is slightly inclined towards liking Bob and associate a number 60 to the part that she likes him and 40 to the part where she doesn't like him. Now Bob makes a measurement. Sadly, it's an unlucky day for Bob. The outcome turns out to be a 0, which means Alice doesn't like him. Should Bob lose all hope? Of course not. Bob can apply gates or transformations to change Alice's state. One such transformation is the Hadamard gate, where he can play a guitar to charm Alice again and confuse her again. A Hadamard gate takes a 0 state into an equal superposition of 0 and 1, thereby raising Bob's chances to 50% again. Now you know about the basic elements of a quantum computer. A confused Alice represents a qubit in superposition. Bob asking Alice represents a quantum measurement, which helps us get the final outcome. And finally, Bob playing a guitar represents a quantum gate, which can change the state of qubits. The power of a quantum computer is derived when we combine all these elements and have multiple qubits. Let's say multiple Alices, which interact to give rise to something called quantum entanglement. So you may ask, how do we use a quantum computer? What is it useful for? Let us look at this very simple molecule of beryllium hydride. This molecule has 6 electrons, and the stability of the molecule is decided by how these electrons arrange themselves. So a very natural question is, what is the most stable configuration of this molecule? Turns out this is an extremely difficult problem for our classical computers, but not so for our quantum computers. So how was this problem actually solved in a quantum computer? Let's say an IBM quantum computer. We start with 6 qubits in the state 0. The next step is we apply gates similar to the Hadamard gate that we saw, and some gates that create entanglement. And finally, we measure to find out the actual result. So I hope, after this story, when you find someone in superposition, you'll go ahead and make a quantum measurement and find your own result. Thank you.
Let's hear it for Aditya Jain.
It was amazing. There was energy in the crowd, and I loved it.
And that's not the last you'll hear from Bob and Alice. It turns out they are a very popular quantum couple. But I'd like to introduce you now to finalist number 4. He is a first-year graduate student in physics at MIT. And before he joined MIT, he spent a year doing research in Austria with a team that was investigating quantum entanglement. That experience also taught him to ask for directions and order meals in German. And now I'd like to welcome Calvin Leung to the stage.
Hi, everyone. Raise your hand if you like money. Great. Keep your hand up if you own a bank account. Keep your hand up if you want to give me the password to your bank account. When you click that sign-in button, how do you know that there isn't a hacker waiting to steal your password? In the future, we can use quantum entanglement to keep your information secure. Quantum entanglement is an unbreakable link between two quantum particles that play by quantum rules. But how do we detect entanglement and use it for our benefit in the real world? I'm going to show you how today using a casino game. In this casino game, there are 2 players, Alice and Bob again. They're each going to have one of these big dice, which have 3 red faces and 3 blue faces. They're going to play this game by going to opposite sides of the casino with these dice, where they meet a dealer. Each dealer is going to flip a quarter, and then Alice and Bob will roll their dice. If the quarter comes up heads, then the dealer will read the color of the dice from the top. And with tails, the dealer will read the color of the dice from the front. So in this particular game, Alice's dealer gets red, and Bob's dealer also gets red. You win when your colors match. Great. Alice and Bob win this game. But there's a catch. If both quarters come up tails, then matching colors makes you lose. Since these dice are half red and half blue, there's an overall chance of winning of 50%. But what if Alice and Bob want to do better? Let's say they cheat. Let's say that when they throw these dice, they have the amazing power to control exactly how it lands. Then every time they play, they can match colors every single time. But they can still only win 75% of games they play, because they don't know when 2 tails are going to come up. Now, this is all classical physics. You might be wondering where quantum physics comes into the mix. Atoms are quantum particles, but they're actually a lot like dice. They have a property called spin, which is either clockwise or counterclockwise, just like red and blue on these dice. And you can measure the spin in 3 possible directions. If you have 2 atoms, you can entangle them with a laser pulse. And then you can play a quantum version of this casino game. Let's see what happens. Remember that in the classical world, the best you can do, even with infinite power, is 75%. My lab group did an experiment not with entangled atoms, but with entangled photons, and we got 83%, which is classically impossible to fake. We can use 83% as a security system that's so tight that you can trust it even if you bought it from your worst enemy, since there's no way in the classical world to fake 83%. This is the world's first quantum satellite, launched in 2016. In the future, I can talk to the satellite, which can talk to my bank. Me and my bank can play the game. And if we see 83%, then we know we're safe. Thank you very much.
Let's hear it for Calvin Leung.
I actually got the chance to talk to a research scientist from IBM who wants to collaborate on making visualizations of what I presented. And so for me, that's like the real prize. That's really exciting.
That was an extraordinary set of talks. And now our judges have to do their very difficult task of choosing our first and second place winners. So our judges will go off to their deliberation room. And while our judges are off deliberating, now it's your turn. You have to tell us who you thought did the best job in just 3 minutes of opening your eyes to some insight into the quantum world. So we're going to have some text voting. You have 3 minutes to text in your votes.
My I've actually never had any exposure to quantum science, so that was an eye-opening experience.
I like that the young people are doing all this research.
They like what they're doing. They give some good examples.
Quantum physics is usually a very tough topic for like regular people to understand, so like giving examples that people could relate to was very helpful.
I found it really interesting, and I definitely am now inspired to kind of look up more about quantum.
Less than 1 minute to get in your text votes.
It was incredibly difficult. I mean, they all did a fantastic job.
There were some fun moments in almost every talk.
There were some really new analogies I'd never heard before.
It was difficult, but we all were pretty much able to come to consensus.
I missed it turning to 0. Time is up. The text voting is closed. We actually have a tie, an exact tie for our audience choice winner. So the first of our 2 audience choice winners is Sue Shi. Come on up, Sue. Congratulations. The second winner of our audience choice prize tie is Calvin Leung. And now, are you ready to hear who our judges picked? Okay. So, Joe, tell me, did you guys have a tough time making a decision?
Yes, definitely. It was a very difficult time, but after we talked over and over, we finally came to a conclusion that I think we're all happy with.
Excellent. And do you have any words of advice or any words for the contestants?
So I would say thank you very much for giving these excellent examples of how to explain things from the quantum world using very plain language and very plain examples. I think that was the one thing that the whole judging committee really liked. And I think the great thing for us is not only could we learn from your examples, now we can steal them and use them on our own, right, and to teach other people and feel smart. Of course, we will always attribute where those ideas came from. So thank you very much for the inspiration with your presentations.
Well, thank you, Joe, and thanks to the whole judging panel for your hard work. Okay, are you ready to find out who won first place for the 2019 Quantum Matters competition? Okay, the winner of the 2019 Quantum Matters competition is Sue Shi. So, Sue, how does it feel to be today's champ?
Feels great, and I also can explain where all of the effort went into this competition instead of writing my thesis.
Well, at least you're already in at Brown, so.
I think she did 2 things very well. She picked the right amount of information to try to convey in the time that she had. And on top of that, she picked really creative analogies, things that I really hadn't heard before.
Well, I want to thank one last time our finalists. I also want to thank our judges, all of the volunteers who helped out here today, and all of you who came to enjoy our Nano Days with a Quantum Leap. I hope you have a fabulous rest of the day here at the museum. Thank you very much.
I do have a book, Quantum Mechanics for Babies, and I have read it to him. He seems to like pointing at the dots and saying, Dad.